All right, so overall, I was really happy with the exam performance. This was a more challenging exam than I sometimes give for midterm 222. I wanted to raise the bar and sort of see where people landed. And my impression from this is people understand linked list, which is awesome. I don't know if the class is like just really exceptional or if the strike helped or what, because we ended up spending an extra week on linked lists basically. But whatever it is, people seem to understand how to use structures and pointers to structures, how to dereference, how to manipulate memory and write code that corresponds to those manipulations. That's the whole key to this course. So I think as a group we're in fantastic shape and we're all set for moving on to trees either later this week or next week, which is the biggest part of the course and maybe the biggest part of data structures. So I think it'll be good. And it's a fun subject too, so. So the last question was definitely more challenging than the others, okay? I wanted that out there to see how you could sort of think about this stuff on your own. It's using stuff that we've already talked about and already worked with, but in a different way. Don't stress too much over the grades, okay? If you come out of this with a 60-something on this exam, that's still a passing grade, okay? Because that last question was 20 points, right? And that question alone can take you from like a 65 to an 85. So, having said that, if particularly after we talk about this stuff, if you're concerned about something, if something's not making sense, come and talk to me. But also as we go through this, right, ask questions while we're going through it right now, and we'll make sure that this all makes sense to you. All right, so question one was playing around with a structure and setting up fields and things like that. And not a whole lot to worry about in the first part other than the character array. So, and also, I had a typo. I asked about a structure named node, and then I asked you to create a structure named data. And that confused some people. That was just typo on my part. So if you got confused by that and you did something accordingly, I tried to give you credit. For example, some people made a structure named node and then created a type def named data. And at first I was like taking off points for that, but then I figured out what's going on. So my intent was just to have a structure named data. So struct is the keyword. Data is the name of the structure, and then we list the fields. Okay, first field was a string called name with no predefined length. You can't say character name bracket 10, that limits you to 10 characters. So the only way to make a general string without fixing a length is to say car star name. But remember, that declares name to be a car star, but it doesn't give it a particular place to point.
So in our structure, the string isn't given a length. How does that allocate enough memory?
It doesn't allocate any memory.
So does it just give it a random spot and link it to whatever?
It's probably equal to 0, but when you create a node of this type, it knows it needs 8 bytes for this because this is a pointer.
Oh.
Doesn't matter how long it's actually going to be storing characters. So yeah, you can find the size of the structure without knowing how long name is. All right, single character named my car, so that's just a car. My car. Integer named val, that's pretty straightforward. And then an array of 10 integers named numbers. So integer, and then the name of the array. And then the number of elements you want in that array. This is always the number of elements you want in the array. So for an array of 10 numbers, this has got to be exactly 10. The 2 points of confusion about this are, one, if we're indexing this array, the last index we can use is 9 because the first index is 0. So we can index it with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The last index is 9. But we want a 10 in here to say hold 10 integers. The other confusion here is with strings. Because if we want an array of 5 characters, we would say character array bracket 5. But if we want a string that holds 5 characters, remember we really want an array that holds 6 characters because we want an all terminator at the end. So with a string of 5 characters, we would want an array of 6, so we would do, array bracket 6. But for integers or anything else, or just plain old characters, this is the number of things in the array. Strings are just kind of a weird special case. All right, so that declares our structure, and then we wanted a variable named code of type struct data star. So close out your structure statement. So struct data star code. And you can put that star right at the end of data, right before a code. You can put spaces on either side of it. You can have no spaces at all. It doesn't matter to the compiler. And then a malloc statement to have code point to a block of memory large enough to hold a struct data. So this is just our usual initialization we would do after a declaration. Code equals malloc. And you need to tell it how many bytes you want to allocate. And I asked you to use size of because that's the only way to know how big this structure actually is. So it's just size of struct data. And that's generally bigger than just a pointer plus a character plus 11 ints, because there's padding inside these structures and stuff. And I don't think anybody did struct data star, which is great. All right, and then code to initialize the various fields. So my car should be initialized to J, so code we need to dereference. So code arrow my car, right? The thing pointed to by code, which is one of these, and then pick off the my car field. So for a character, it's single quotation marks. For a value, it's just an integer. For the 2 array references, it's just like this. Right, and bracket 1 equals minus 999. And then the more confusing part is the name. So we want the name to be equal to Sally. And there's a few ways you can do that. Here's a simple way. Right, that will absolutely work. Now, why does that work? Because in C, if you write double quote Sally, close quote, what happens? The compiler will make sure that when your program runs, there is a chunk of memory somewhere, which is big enough to hold Sally in an all terminator. And at the first location of that chunk is the letter S, followed by A, 2 L's, a Y, and an all terminator. That gets set up for you by the compiler and the linker. And quote Sally means the address of that letter S. It's synonymous with the address of the first character in that string. So when I say code arrow name equals, it's taking the address where Sally is stored and it's saving it right here in this variable, which is said to be a pointer to a character. Right, or you can use string copy. And again, this is the address of a location in memory where Sally is stored. String copy reads from this address into that address up to and including the null terminator. But if you just do this, you'll segfault. Because code arrow name, that's the value of this name field, doesn't have a value. We've declared it, but we haven't initialized it. So you need to initialize it. Using malloc. And we could just hardwire 6 bytes because we know we have 5 letters in the null terminator. So that'll find us 6 bytes in memory, and it'll then copy Sally and a null terminator into that. Or you could malloc 6 times size of car, if you wanted to make sure that characters were 1 byte. Or you could do string length of Sally plus 1, which is where 6 came from. Because string length will tell you the number of characters, not counting the null terminator. Add 1 for the null terminator. So different ways to do it, but same effect. All right, not a whole lot in there that seems to trouble people. All right, question 2. I was looking for a function that would go through this linked list with the funny looking nodes and return the sum of all the temp fields, excluding the sentinel. And so this is going to include snippets of code you're going to write again and again and again anytime that you deal with lists. So let's make an integer valued function named count. It takes in a sentinel node. So we want a temporary. I'll call it temp node. I could malloc. I could call malloc size of struct node and set temp node equal to that. And if I want to create a new node, that's exactly the right thing to do. But we have a list already in memory. We're being told where the sentinel of that list is. And really what we want to do is follow the list from node to node, starting at the sentinel, add up the data fields that we find, and then return that number. Nothing in that requires us to create a new node. Okay? We're going to make new variables that will point to nodes in our list, but they're pointing to things that already exist. That's your key that you don't need to call malloc. Okay, if you need to make a new node, if you're trying to insert something, or if you wanted to make a copy of a node to do something with it, right, then you might need a new node. That's when you call malloc. But just making a new variable to move through the list, no need to call malloc. And if you don't call malloc, you definitely don't need to call free. So I'm going to start off with a struct node star temp node, and I like to start with the first thing in the list, the first data node. So I'll set temp node equal to sent arrow next, and my comment, which you'll see again and again, is first data node or null if the list is empty. So my mental picture, temp node is pointing to the first node that I want to consider. And I'm going to do something as temp node moves through the list, and I'm going to stop when temp node is equal to null, because that means I've fallen past the last node of the list. So my while statement is just while temp node is not null. And if my list is totally empty to begin with, first time I do this assignment, temp node will be null. I won't do anything in my while loop. I'll never go through it even once. All right, so this is a nice little loop in here that's going to visit every node in my list, starting with the node after the sentinel. What do I want to do? I want to grab the temp field from that node, add it to a running sum. So I'm just going to do sum equals sum plus temp node arrow temp. And at that point, I remember I need a running sum, so let's initialize that. Let's declare it and initialize it to 0. And if I never go through my while loop, my sum will be 0. that's the correct thing to return for an empty list. All right, otherwise, deal with the node that I'm looking at, temp node, and then move down the list. So temp node equals temp node next. And when you come out of your loop, just return your sum. Alright, so you definitely need a loop in here, right, because we don't know how long the list is. So we've got to iterate until some condition. We need a running sum. We need to use arrows instead of dots, because everything in sight is a pointer. And usually everything we do in data structures is a pointer to a structure. So we're almost always using those arrows. It's pretty unusual we would use the dot notation. I'm skipping over the sentinel. I'm making sure I include the last node. Okay, those edge cases, most people nailed it perfectly. So good job. Starting with the first node after the sentinel, counting the last node, and then not going beyond the last node. If you got that, that's perfect. Make sure that you use null. Don't use 0. Okay. Null is equal to 0, but it's actually a pointer whose value is 0 and of a type that's pointing to void. And if you use 0, you'll probably at least get compiler warnings. But if you go to a different machine where 0 is a valid memory location, null may not be 0 anymore. Right? Don't ever use magic values, especially if they're not magic values you created. Okay, null is set up in standard io.h. When you include that, you're guaranteed null is the correct value. So always use null. People will really raise eyebrows otherwise. All right, I think that was all I saw for comment in there. So question 3, linked list analysis and manipulation. So first part, what will be printed by the following statement? Okay, I'm going to throw some possibly slightly imprecise but hopefully helpful labels on top of these nodes. This is LL, right? That's the sentinel node. LL arrow next is really the address of this node with a -1 in it. LL arrow next, right? Well, I mean, that's the value stored in this box, but it's really the address of this. And so if I'm printing LL next data, well, this is LL next, the data field is equal to 10. And then a space, and then LL next data. This is LL next, its data field is -1. This is going to print 10 space -1, and then a new line. This node at the end would be LL next. And so if you printed LL next data, you would get your 50. All right, and then write some C code to delete the last node of the list without using any loops or conditional statements. The reason I do that is because inevitably people will, with this kind of question, they'll copy their delete function from a programming assignment that they have on their notes, and then they'll call delete with an argument of 50. Technically that will delete the 50, but it doesn't show me anything about your ability to do this on a test. So that's why I do these without loops or conditionals. And it's easier to do it without loops or conditionals than to write a general delete function. Okay, so how do we delete this 50? We basically need to change this field here to be a null, and then we need to free this location here. Okay, so to change this field to be a null, well, this block is LL next. So if we said LL next, next, next equals null. That puts a null right in here. That makes the list end after the 10. We also want to free this last node. Well, what's the address of this last node? That's LL, next, next, next. And we can't free that after we change it to null because we'll be freeing null, which is a seg fault. So I'm going to set this as an argument to free first. And you can wonder, is it okay to free LL next, 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 and then try to use LL next, next, next? Absolutely. Okay, because in this case, LL next, next, next is the contents of this block. Okay, the next field of this node 10. That's what LL next, next, next is. It's a number, it's a location in memory. Here I'm saying free what's at that location in memory. That gets rid of this 50. And now I'm saying take this block, this bottom piece of this node, and set it equal to null.
So that first statement,
Mm-hmm.
you're basically freeing the actual node itself.
That's freeing this node here, the 50.
The actual node, yeah.
Mm-hmm.
And then the second statement, you're just changing the next field of the node before.
Exactly, exactly. So this first statement frees this from memory, and then the second statement sets this field on the prior node. And that's exactly what you need to do to delete a node. Now, if you don't want to think about next, 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 right, another way to do this is, you know, I'm just going to use SN star for struct node star. Make a struct node star first equal to LL next. So this is first. Make a struct node star second equals LL first. So this is second. Make a struct node star third equals, sorry, this is first next. Make a struct node star third, which is second next. So this is third. And now it's very straightforward to do what we're trying to do. What are the two things we need to do? We need to set this box equal to null. So that's just second arrow next equals null. And we need to free this node. That's just free third. And we can do those two statements in either order. Neither of them affects the other. But what are we freeing? We're freeing third, which is second next, which is first next, next, which is LL next, next, next. And second next equals null. That's saying first arrow next equals null. That's saying LL next, next, next equals null. So they're the same thing, but the way on the right to me is clearer because I don't have to keep track of counting these things. All right, and then write some C code to create a new node with a data value of 5 and a variable named new that points to that new node. So struct node star new equals, and we need to malloc because we need memory. And how much do we need? Whatever the size of a struct node is. And then to set the data field equal to 5, that's just new arrow data equals 5. And then last part, insert this new node between the -1 and the 10. Well, if we've set up first and second, it's again pretty straightforward. First arrow next equals new arrow next equals second. All right, so that squeezes it in. If you don't want to do it with temporary variables, first arrow next is LL, next equals new. And then new next equals second, well that would be new next equals LL next. But I'm changing LL next right here. So if I said new next equal to LL next after this, I'm setting new to point to itself. So I need to do this piece first, which would be new next equals LL next. And I have no good way of telling you how to figure those things out, right? It's just practice with pictures. And then go back to your picture and make sure it's doing what you think it's doing. All right, and here we have a linked list, and we're supposed to swap temp2 and temp3. And I asked you not to swap just the data values, but to swap the entire nodes. So here's something pointing to a node, points to temp1, temp2, temp3, and goes on to whatever. All right, swapping temp2 and temp3. Well, basically temp1 needs to point to temp3, temp3 needs to point to temp2, temp2 needs to point to whatever comes after temp3. So the only thing that can get you into big trouble here is the order of operations. Okay. Nothing is pointing to temp1 that we need to deal with. That's always going to be right here. So we're probably pretty safe saying temp1 next equals temp3. We don't need the old value of temp1 next because we know that's just temp2. We've got a variable pointing to that. So temp1 next equals temp3. That's a good one to go first. Let's just move down sequentially. Temp2 next should be what? Temp2 should point to the thing after temp3. Because temp2 is going to go right here where temp3 is. So temp2 next should be temp3 next. And temp3 should point to temp2, so I need to change temp3 next. Well, if I do that up here, then this statement I just wrote isn't going to work. So let's do it after we set temp2. Let's set temp3 next equal to temp2. So let's throw some numbers in here. And let's see what happens as we do these things. Temp1 next equals temp3. Okay, this arrow is going away. Temp1 is pointing to temp3. Temp2 next equals temp3 next. Temp2 next is this arrow right here. Let's change that to point where temp3 is pointing. That's going to go right here. And then temp3 next equals temp2. That changes this arrow to point to temp2. So what does our list look like? We come in from here on the left, we get to node 10. That takes us to node 30, which takes us to node 20, which takes us to whatever the rest of the list was. That's a good swap. Now suppose we did this differently. So suppose we do this first. Temp 1 next equals temp 3. Okay, temp 1 points to temp 3. That's good. Suppose we do this second. Suppose we do this second. Temp 3 next should equal temp 2. That changes this pointer to point to temp 2. And now, let's do this third, which is also an error, and say temp 2 next equals temp 3 next. So temp 2 should point wherever temp 3 is pointing. That's right there. Okay, now check your work, follow the list. Start off here, that points to a 10. That points to a 30, 30 points to 20, 20 points to 20, 20 points to 20. And that's where you get that big long list of numbers that scroll off your screen when you call your print function. Right, really easy to do. So we've got a circular list. Usually means something got done in the wrong order. Right, so do that second, do that third. So you can check these things after you're done, before you code or after. Let me mention one other thing in here. Suppose I said something like save equals temp 3 arrow next. Okay, so I do this first one. The first one's straightforward. I do save equals temp 3 arrow next, and then I do temp 3 arrow next equals temp 2. And then I could do temp 2 arrow next equals save. Okay, that's fine, right? Temp 2 is remembering where temp 3 was pointing. That's the address of this block. Down here I set temp 2 to point to that. That's fine. Here's what is sometimes tempting to do and what doesn't work. So save was equal to temp 3 arrow next. I said temp 3 arrow next equals temp. Suppose instead I had said save equals temp 2. That does nothing useful. I've said save is temp 3 arrow next, and now I'm setting that equal to temp 2. Doesn't that set temp 3 arrow next equal to temp 2? No. Okay? Save is just a local variable. I've given it the address of this following node. Now I've given it the address of temp 2. I haven't actually changed the value of temp 3 arrow next. And that can be subtle or obvious depending on the time of day. Temp 3 arrow next is the contents of this block, this field in the node. This sets save equal to the contents of that. This sets save equal to the address of temp 2. Doesn't change the contents of this block. This is like saying x equals y, x equals 0, y doesn't change value. But when I say temp3 arrow next equals something, that's saying temp3 arrow next, that's the contents of this block, set that equal to something new that actually changes the value. If that seems obvious, good. If it seems confusing, good. If it makes no sense at all because you thought this would change temp2, that's also good. Right? There's no bad side here. Just go ahead and draw some pictures and think about it. Right? Think about what's happening in memory with each of these statements. Eventually, you stop thinking about memory. You just work with this intuitively. Oh, this is just temp3's next field. It's equal to temp2. Right? But while you're continuing to refine that intuition, right, little things like this can pop up. Right? That's okay. You can always come back to actually thinking about the memory itself through pictures or through the debugger. But then eventually, in whatever way each of our brains codes it, right? Temp1 just means this node, temp1 next is this, but we know how to use it without doing things like that. All right, so question 5, the reversal of the list. So you're given a standard linked list, struct node, usual form, list of integers with a sentinel node, and you're writing a reverse function which should create a new linked list containing the nodes in reverse order. Okay, so new linked list, you can't use the original sentinel. You got to make a new sentinel, and you can't just change the links in the original list to point in the other direction, because then you're destroying the original list. And I had a note on the board, don't change the original list. So you're creating a new linked list using the data you find in the original list. And there was a hint of pseudocode on how to do this, which is basically make your new sentinel node. Let's call this original. Right, and let's say this is, you know, A and B and C and Z, and here's our original sentinel node. Okay, one way to construct the reverse list, start with an empty sentinel node, okay? Take the first node in your original list, add that immediately after the sentinel. Take the second node in your original list, add that immediately after the sentinel. Take the third node in your original list, insert that immediately after the sentinel, and so on until you get to the last node. Insert that immediately after the sentinel. And now if you look at your new list, the sentinel points to the last thing you inserted, the thing before, C, B, A. That's the reverse list. So there's a few steps. Make a new sentinel node for the reverse list. Start traversing your original list. We've done that a few hundred times. Traverse your original list. Each time you find a new node, create a new node for your reverse list. Copy the data value, insert it in the beginning of the reverse list. When you hit the spot where you're out of nodes in the original, return your reverse sentinel. And I granted some wiggle room in here. Some people assume that the list contained at least one data node, which it doesn't say anything about that, right? If the original list is empty, reversing it is just also an empty list. But it's kind of an edge case, so if people got tripped up on that, I didn't take off points for it. Some people returned null if there was no data. Well, you still want to return a sentinel, but that, you know, might have been specified more clearly, so I didn't take off for that. So I was looking for general strategies in here. But here's something we could do. So struct node, reverse. struct node, and I'm going to call the original Sentinel original. All right, so what do we do? Let's make a struct node. A reverse. And we'll malloc size of struct node, call that our new Sentinel node, and set rev next equal to null. So rev is a Sentinel node of the new list, the reversed list. Make a struct node temp equal to original, arrow next. That's first data node, or null. And then iterate while that's not null. So if temp is not null, temp is the next node in our original list. Let's make a new node with the same data value and put that into our new list. So struct node new equals malloc. And then set the data field. So now it's got the same data value as the original node, and now we want to insert it in the beginning of our new list. And this is the usual. Take the new Sentinel node, have it point to the new node. There's my handy comment. And we want the new node to point where the Sentinel was pointing. So since I'm changing where the Sentinel is pointing here, let's do this before we make that change. Let's have new next equal reverse next. So our new node's pointing to the thing that comes after the Sentinel. And then when we change the Sentinel to point to new, new comes before what was in the beginning of the list. So that inserts into our reversed list, move down the original list. And when you're done, just return the reverse list. So things to think about, right? We don't need a temporary node pointer. We can actually use original as our temporary because everything is passed by value. If I change the value of ORIG in this code, it's not going to change anything in the calling program. If I change star ORIG, that's a different story. But ORIG itself is just a temporary variable that holds a memory location. So I could actually use original equals original next while original is not null, original equals original next, and so on. So you'll see that sometimes. This works if the original list is just a Sentinel node, because rev will start off as a node with a next field of null, and if original next is null, I'll never go through my while loop. All I'll do is return that empty Sentinel node. So you don't need to handle that as a special case, although some people did. It doesn't hurt to do special cases if it's clearer to you or you want to make sure. That's fine. All right, so just for future reference, right? Here I was asking for a function. So you need to have something that starts with struct node, reverse, parenthesis, argument list, curly bracket, and then some code. Here I was asking for some C code. Okay, could be a function, doesn't have to be a function. I was just looking for some lines of C. Here I was looking for some C code to do manipulations. Here I was looking for a function. And here we were just writing some code or doing some analysis. If it says write a program, then you've got to have a main program. It's got to be a main. If it's going to have arguments, it's got to have an argc, argv kind of arguments to it, and so on. Function should be a function name, curly bracket, all that stuff. Some code is just lines of code. And you can always ask if you're in doubt, but you can save yourself a fair amount of time if you don't have to write more stuff that you don't need. All right, so tomorrow I want to talk about the main program for PA3, because there's some confusion about what is or isn't part of the main program. So I want to go through that in some detail, and then we'll start talking about queues, which will be parallel structure to stacks. And then we're going to start talking about trees, and trees will be sort of the biggest data structure we deal with in here. It's probably the most popular data structure you'll encounter in general, and we'll use them the rest of this course. We'll use them a lot in 223. So we'll start talking about that probably tomorrow or Wednesday. All right, so I'll see you next time.